Hello everybody, this is Mohammad Abdulaziz and this is the fourth tutorial of the Functional Data Structures course. I hope you enjoyed the previous ones and I hope you enjoyed this one as well. So I will start with solving the first problem in the fourth sheet. So suppose we have a tree whose members all belong to a linear order. So for example, all natural numbers or integers. We want to define a function and implement a function that takes a tree and two arguments of the type of the elements of the tree. So you get a tree and two types that are both of type A. So you have an A tree and two elements of type A, and you want a list of elements from this tree such that the following thing applies. So this list is basically a sublist of the in-order traversal of that tree that conforms to the following condition. All members of it are greater than the first element A and smaller than, greater than or equal than that one, and smaller than or equal to that one. So let me just show an example to make sure that it is clear what I'm talking about. So we have a tree like that, an order tree. Okay. And I want, and you're given, for instance, if we're given 2, so I'll call this 3. So the function that we have is called in range. So in range of t and 2 and 4. Okay, it should give us a list that has the following members. So it should go as if you're going in order, but you're going to only get elements that are greater than or equal to the first argument, which is 2. So you're going to get like this 2, and then this 3, and then this 4. Okay, so 2, 3, and 4. In particular, we want this function to not descend into a node if you know that this node is out of the range. So for example, here we're saying in range of 2 and 4, of t and 2 and 4. So you're going to this is 4. So okay, you know that this element should be included, but you also know that you should not go to the right because going to the right will take you to elements that are greater than the upper bound of your range. And similarly, so you go to the left, and then you know 2 is basically the smallest element in your range, so you cannot go anywhere to the left, and then you will only go to a 3 and then include it. And when I'm saying you're going to start here and then go that way and then go that way, this is just an abstract description of what happens, but what we really need to write a precise recursive definition that does that. So given the tree and the range, you should start at the root and then descend in a way that avoids going into any node that will be outside of the range, and then return the list of elements that you have encountered in the way they would appear in the in-order traversal. Okay. So so for example, the in-order traversal of that thing will just be 1, 2, 3, 4, 5. So this is 2, 3, 4. So the elements here are in the same order in which they would appear in an in-order traversal. Okay. So let me write the function quickly, but I want you to pause actually and write it yourself. I will write my own version here. So do that. Okay, so the first case will be when the tree is empty. So let me just see what is going on there. In order tree. Oh, so we are actually supposed to get the you're supposed to import that file that we also imported last time, bst demo. This is called. I think I don't have it in the directory correctly, so I'll just get it. Okay, we have the file now, and accordingly we have the type. So let's see what's going on there. So in range of the empty tree, and any two things should be the empty list. Okay, and after that we have the other case, and as I said in the other case, so as usual, firstly I'll just write the other case here. So it's going to be node LAR, and then U and V, for example. Okay, so as I said, we are going to only descend to the left or to the right, depending, in a way that ensures that we will not descend into nodes that are that are outside of the range. So the way we do that here is, firstly we would go. So we would say if if A is if U is strictly smaller than A, what that means is that the element, so for example here, if like in the example that we have there, we start at this element, and we see, okay, this is going to be A, and so A is 4 and U is 2. So if 2 is strictly less than 4, which is the case, we should descend to the left, because the elements to the left in the left subtree might have elements that are actually smaller than A, that are bigger than greater than or equal to U, which means that they are in range. So we say that. So if U is strictly smaller than A, then we get the elements on the left tree. Okay, so in range of L, U, V. Okay, else we get an empty list. Okay, and then we want to append that to the result of firstly I'll just say, so this should be appended like that, and then I want to say, and then I want to do a check on the A to know if I should include it or no. So if A if A is greater than or equal to U and A is smaller than or equal to V, then we shall include the A, otherwise we shouldn't. And then the last case here, this is where we would descend to the right hand side, to the right subtree or no, and that should depend on whether A is strictly smaller than V, and in this case we go to the right. Okay, so let us try this. I'll just do the same and construct the tree, and then apply this function to that example tree. So we have 1, 2, 3, 4, 5. Okay, so node K 1, and then another 2, and then another node 3. Okay, and and then this is also a subtree of something else, whose root is 4, and has as a right subtree another subtree, as a right subtree a tree. It has one element that is 5. Okay, so that is that one, and then let's see in range of that function. So it doesn't work because range node. Oh yeah, because I didn't give it the other arguments. So we have 2 and 4. So 2, 3, 4, which is like the example there. Okay, so now we need to prove that if the tree that we're given is an ordered tree or a binary search tree, the set of elements in this given list is going to be the same as the set of elements that are within that range and that belong to the tree. So this function here, as we have said earlier, is a function when you define a certain type, you get a function set underscore whatever the type name is, and that function gives you the set of elements in that type. So for example, you have set tree here because we have a type called tree, that gives you the set of elements in that type. So for instance, let me just show you. So set tree there, it's all the elements here in that thing. So 1, 2, 3, 4, 5. Okay, so let's now do that, prove that lemma. Okay, so this function here, we have the function in range. So again, I'll suggest you pause and try it yourself, but always continue. So this function in range here is defined in a primitive recursive way with respect to the given tree. And what that means is that we can just prove things directly by induction on the tree. So let's see induction T, and I'll just try O2 and see what happens if it doesn't work. Okay, so the first lemma just goes through very easily. The reason I did the induction on T is because the function is primitive recursive. Look here, empty and node, so it only matches on the type and exactly the type constructors. So the second lemma, in the second lemma, we need to prove that, so this is slightly fancier than the earlier lemma. So here there's this function filter that takes a list and a predicate. So it's a higher order function. It takes a list and a predicate and returns to you a list that has the elements from that list that satisfy that predicate. So for instance, in this case, what we have there is this will return to us that, like, given the in-order traversal of T, we will only return the list, return a list of elements that are greater than U and smaller than or equal to V, in the same order they occurred in that list. So let me show you by an example. Like for instance, so this is a stronger lemma than the previous one. So the previous one only stated that the elements in the tree are the elements in the tree, that the elements in the return list of the in-range function all occur are exactly the elements from the tree that are within the range. But the second lemma wants us also to say that in-range actually not only gives you this exact set, but also gives you this exact set in the exactly right order. So let me just show you a simple example of what filter is. So for instance, if I write filter x greater than or equal to 3 and apply to 2 and 3 and 4, what that should give me is the element 3 and 4, because it will go recursively on each member of the list and see if it satisfies the given predicate. Of this predicate is on the expression expecting an x and returning true only if x is greater than or equal to 3. So here we would have 3 and 4, for instance. Okay. So let me go to the proof of that lemma quickly. I think it's an easier lemma. It's not a very difficult lemma. You don't need another lemma for it. But in case it's not complicated. Okay, so again, I will do it by induction on the tree. Okay, and then let's see what O2 tells us. So O2 does not terminate here. Okay, and let's stop it then and see the induction hypothesis as it is. So here in this exercise, I'm telling you that you will need to use filter empty conv, and what that lemma basically tells you that. Let me just write it there and show what it tells you. So if the filter of a certain list is empty, then this means that every member in that list violates the predicate. Okay, so given a filter and a predicate and a list, if that is empty, then this means that every element in the list violates the predicate. So let's see here in this proof. So 1 second there. So we need some lemmas there to simplify this non-termination by auto. Let me just see how it works. If it will terminate at all, and if it doesn't, then we're going to try and get the lemmas directly from here. So we need to. So firstly, we need to understand the reason for this looping there. So yeah, so it actually doesn't. It ends up terminating at some point. So it's not. So let's see what what do we have here and why it's not working. So here we have. Okay, so basically we need to say that if this is a singleton, so here we have this lemma, and this lemma does, like this sub goal doesn't need anything from the induction hypothesis. We only need to say that if you have a singleton that is equal to a list appended to an element and another singleton, then this means that this list is empty and that list is also empty. Okay, so let's prove that lemma. So that lemma should be like that. X's, Y's, sorry, X and Y's. Okay, let's head down there. Then what that means is that X's equals empty and Y's equals empty. Okay, so let's do that. X's. Okay, so that's this lemma. Okay, and now what I want to do with it is to simplify that goal there, that sub goal there, with that lemma to get to know that the two filters are empty, and then we'll get the first sub goal out. But let's just wait. Sure, I can show you. Okay, so we want to rewrite that into basically v equals v, and that should be done if we add this to the sim set. Let's see how it works now. Okay, so now we want to say that what we want to show. So we now have the current sub goal says that filtering from this, the left subtree equals empty. Okay, so this is the left subtree and this is empty. We want to prove that the left subtree has no elements within range if every element in the left subtree is smaller than v, when v is the lower range. So if every element is smaller than in the left subtree is smaller than the lower element in the lower bound, then the filtering, that the in-order traversal of that subtree should be empty. Okay, and this is where we will need that lemma. So this is going to help us rewrite. So look here, we want to like our goal is like that. We want to change it into this, and then this will be proven by an assumption. So we want to say that we want to change this into saying that we want to change this we want to rewrite this into a statement saying that everything in the in-order traversal of T1 doesn't fall into that range, and then that should follow from this. So I'm going to add this lemma to the sim set. And let's see. Okay, so now we have less sub-goals. Instead of 18, we only have 8. So this is, so what should that be? So here we have, we want to say again that everything in the left subtree, filtering the in-order traversal of the left subtree also returns empty. And why should that be the case? Because if we have something x2 that is strictly less than the lower bound, and everything in the left subtree is strictly less than x2, then of course that should hold. So in this case, we want to use that lemma, but the problem is that we need to flip the direction of those two of the empty to get the empty to the left, and to get that to the right, in order for it to match the sub-goal and the for simplifier to work. So I can do that quite simply by proving us a lemma, a simplification rule that says for any predicate, the filter of a certain list. I'm just going to show you this flipping and writing as a lemma. Okay, and this should go simply also. Let's see. Okay, and let's see now what's going on there. So now we only have one sub-goal. So what is the one sub-goal? So basically we need a contradiction there. Yeah, like we need to show that, like if we have the false in the conclusion, this means that we need to show that these assumptions have a contradiction in them. So here we have that the lower bound, everything in the left subtree is smaller than the lower bound u, and everything in the right subtree is greater than the lower bound. Okay. So what is wrong with that? I think this contradiction should be provable just by O2 again. Let's see. Oh yeah, it is. But sometimes O2 it doesn't. Although O2 is supposed to work on all subgoals, sometimes it suspiciously stops because there are certain parameters. I don't really understand why. It's something inside of it. So I think that there are certain looping parameters in O2 that basically prevent to do what is specified to do. So I mean, sometimes you can change them. So you can give O2 those two arguments that will subsume the original parameters or limits on so you can actually check that if you go to the code of O2. But in any case, I don't advise you to do that. Like this is very hacky, and so basically here I gave it the depth of how far it should alternate. So O2 does simplification and the classical reasoning, and it alternates them. And this is the depth of how many times you should do one. You should apply one method after the other. But I don't advise you to do that. I just advise you to use the things as they are. So if you want to apply any method more than one time, like as many times as possible until the proof either terminates or the method fails, you can just put a plus. So here, instead of saying O2, I just said O2 simp in the same command plus. Okay, and I think actually fast force might be faster for that goal. Let me see. So it's the first one. Let's see how the second one will go. Yeah, it is faster. You can, so let me just show you another thing there. So plugins, Isabelle, timing panel, okay? So this thing, you can use it to measure, to see how long will a command take. So it tells me the slowest command is something that took 3.6 seconds, and it's this one basically. So if I would change this to fast force and to this, and so this fast force call handles the first sub goal, and this one handles the step case. So the base case, the step case, and then it just tells me that it took half the time basically. That should be enough. Okay, so that's the end of the first exercise. So I will go now to the third and last exercise. So we need to generate a set of all trees of a given height. Okay, so that should be the function signature. Okay, and I just want to clarify a few things. So here, when I say unit tree, what that means is that it's a tree whose elements are of type unit, which is basically in a type that just has one element in it. So it's informally you can just call it a dummy type. So it is a tree. So it's the type that only has that element in it. That's the only element in it. Okay. So unit only has that element. Okay. So I want to generate all trees of heights. And all trees of heights smaller than or equal to n. Okay. So let me do that quickly. So enumerate of 0 should be the empty set, okay, and enumerate suck n, which is the way you should do recursion on natural numbers, should be the tree whose height is suck n union all the trees whose height is n. Okay, so sorry, the set of all trees whose height is exactly suck n, and that should just be specified right now. So let me just show you another function. So the function is the union function. So let me just show you that. So it is union, okay, and that takes two sets and gives you the obvious thing. So let's just do that. Okay, so I think yeah, if you write a binary operator, I think you have to write it that way. Yeah, you have to write it between parentheses. But so that function, so basically should give enumerate all the trees that are of size n, union all the trees that are of size suck n, and all the trees that are of size suck n will basically be the following. I will write it as a set comprehension there. So you have tree t, and actually you don't need. You can write it. You can just say node enum, node L, and then the root of type unit, and then the right subtree, and then I say here L is in enum n, and R is in enum R, okay, and enum n as well. So basically they are all trees that are of size n. So all trees of size suc n are going to be the trees that are going to be the trees formed by a root and any tree of size n. Okay, so and the way I'm actually wrote the comprehension without explaining what that means. So here, this is the set comprehension that says all trees of such that this tree has a root that is of unit type, like that is the only element of unit type, which is the obvious root. There's no way it can have another root if it's of the correct type. And then the left subtree should be an L, such that this L is of size n, and the same for the R. Okay, that is exactly equivalent to writing all trees such that there exists an L and an R where T equals that tree. Okay, so this comprehension is exactly equivalent to the first one I wrote, but the first one I wrote looks slightly better than that. Okay. So now the proof. We need to prove that this function is sound, and what that means is that it satisfies that. Okay, and here, because we're proving only something about one tree T, and it's the function as the function is primitive recursive over the natural number. The function enum is primitive recursive over the natural number. We can just prove it by induction on the natural number n, and let's see how auto will handle that. Okay, so we have an induction hypothesis here. Let me just go back a step. Okay, so we have an induction hypothesis. Okay, so that will not work because the induction hypothesis talks about a T that is an element in a tree in enum of n, and what we want to prove is about the T that is an element in enum of such n. So we need to generalize over T. So arbitrary T. Okay, and then this is up to auto. So what do I have there? Yeah, so basically I just want to say that, so I have that T is in enum of n, and I know that if it is an enum of n, then its height is less than or equal to n. So what we really want to show that if something is less than or equal to n, then it's less than or equal to suc n. And there is a, let me show you how you search for lemmas like that. So find theorems. So we want to show something that matches that pattern, something less than or equal, something implies something less than or equal suc of something else. And that what we want. That's what we want. So we can just say we can use that like this. Yeah, and it works. But let me also revise with you something else that you must need to soon take in the lecture, or you have taken in the lecture, sorry. That is using this as an intro rule, or as a in the backward reasoning fashion. Okay, so you can apply like instead of doing this more elegant proof, you can do an uglier one. Just to show you what we have here. So here we have this rule construct, and that is equivalent to the application of modus ponens. Okay, and what that is the following. So if I say, let me just go to the paper quickly. So if I say, if I have a goal P, okay, that is my goal, and I have another theorem that says Q implies P. I know that if I want to prove that goal, and I can prove Q, then I have the goal. If I know that if I can prove Q, then I can prove P as well. So a way to do this form of backward reasoning from proving the obligation that P into proving the obligation Q is to apply rule and that lemma. This is the lemma. Okay, and then this will change the goal into Q. So goal now is Q. So this is modus ponens. It's called modus ponens in logic. It's a backward way of reasoning. So the way this happens here is that we had a sub goal there, that something is less than suck of an n, and that's the conclusion of the theorem there, which is equivalent to the P on the paper. And then we want to replace that with just less than or equal to the n, which is the Q in the paper, or that assumption here in the less than or equal to suck I. So then you can say just rule of that thing, and then it will change your induction hypothesis in your conclusion to match the Q, and then it will work. But and then you can just apply auto. But of course, the first proof that I did is better than that. Okay, so that's it. Thank you very much. This one was a little longer than usual. I hope you enjoy it, and yeah. If you have any questions, of course, post them on the Piazza forum. Thank you very much.